Hello everybody, and today we have a very spicy integral from Maths 505, and we're going to be solving the integral from 0 to infinity of cosine of x divided by hyperbolic cosine. We're going to be solving this using complex analysis, so hopefully this should be a lot of fun, and yeah, let's get started. The first thing I am going to do though is just turn everything from in terms of cosine and hyperbolic cosine. I'm just going to turn that in terms of the exponential function, which is e to the x. So we know that cosine here, this is just the real part of e to the xi. Just by Euler's identity real quick, so you have e to the xi is equal to cos x plus I sine of x. And you take the real part of both sides, it's pretty clear that, well, you just kind of ignore that term and you end up getting just, cosine. So yes. But one thing we do need now is to express hyperbolic cosine in terms of e to the x, which really isn't that bad because by definition it is just e to the x plus e to the minus x all over 2. So I'm just going to sub all that in real quick for our integral. Pulling the 2 and the real part out, we have e to the xi over e to the x plus e to the minus x dx. And because both cosine and hyperbolic cosine are even functions, what we can do actually is instead of having this kind of weird 2 out front, we can just change the bounds, right? So we can just say, instead of being from 0 to infinity, we can drop the 2 and say it's from negative infinity to infinity. So over the whole real axis of e to the xi divided by e to the x plus e to the minus x dx, and then the real part, of course, up front. Okay, and what we're going to do here is, this is where the complex analysis begins, really. Because what we're going to do is integrate it over this contour right here. So we're just going to integrate it over the semicircular contour. This way, of course. And yeah, so the reason I wanted to get it over the entire real axis is basically so we can just use the semicircular contour. So yeah, let's get contour integrating. Yes, I did make that a verb. Okay, so as you might know, this integral right here is then just going to be 2 pi I times the sum of the residues of f at some k. This function here, of course, is going to be our f, and our k is just going to be where our residues are. And one of the reasons this actually, well, the reason this integral directly equals the residues is really just because this top bit right here, so like the circular part right here, that part right there, by Jordan's lemma, that is just going to go to 0. If you want to check that, you can, but for sake of brevity, we are just going to, we're going to say it's 0. You can prove it, but just take my word for it, please. So yes, so we have 2 pi I times the sum of all the residues. So the question is now, what are our residues? So the way I like to think about it is basically, I always like to set the denominator equal to 0 when I'm doing this on my own, but I should probably be a tad bit more formal, so we'll do that, I suppose. We're just going to take the inverse here and basically set it equal to 0. And because e to the x by itself is never actually going to be equal to 0, we can just cancel it out on both sides. So what we're left with actually is e to the x plus e to the minus x equaling 0. Multiply both sides by e to the x, you get e to the 2x plus 1 equals 0. I'm just going to kind of rearrange for 2x here. So we get this natural log of -1 term. Now, a lot of y'all might be screaming, oh, look, it's the Euler thing. It's just going to be pi I, to which I would say, yes, you're right. It is, but that's not necessarily the only answer. And the reason for that is because if we take, so basically just consider e to the pi I for a second. This is just -1, we know that. But, okay, what if we took e to the pi I plus 2 pi I right here? Well, by definition, by properties of exponents, it's just e to the 2 pi I times e to the pi I. But this term right here, that's just 1. This is negative 1. So this still equals negative 1. It's the same thing. So basically, pi I, yes, that is a solution, but for finding the solution to this integral, we don't just need one residue. We need all of them. It's the sum of the residues after all, yeah? So basically, what we need to do is express this natural log of negative 1 term in terms of, like, basically, we need to find all the solutions, not just, say, like, this one. So what we're going to do, actually, is express this as pi I, right? That's just the normal solution, plus 2 pi I, n, where n is just some integer. I believe this is how you can express it. Okay, so now that we have that established, we can solve for x. So this means that x, or where our residues are, is going to be equal to pi I over 2 plus 2 pi, or, oh, no, just normal pi I n. And for sake of brevity, because we'll be using this enough to where I don't feel like writing all this out all the time, I'm just going to define that as k. Again, just for sake of brevity. So yes, now we can find our residues, actually. So I'm going to go up here. And our residues right here, it's just going to be equal to, well, I guess they're integral actually, but you get the point. So equals our sum, 2 pi I times the sum. Actually, let's do the residues on their own. So our residues here, go down here. Our residues of f at k is going to be equal to the limit as x approaches k of x minus k times e to the xi divided by e to the x plus e to the minus x. And to evaluate this limit, actually, we're just going to use L'Hopital's rule, or as I like to call it, the hospital rule. Very simply, because if you plug in k here, you get 0 on the top, and like almost by definition, because that's the way we solve for k, you're going to get 0 on the bottom. So what we're going to do here is this is just going to be equal to, I'm just going to product rule the top. Oh. I'm just going to product rule the top, so we're going to have e to the xi plus I x minus k e to the xi divided by e to the x minus e to the minus x. Okay, so I'm just going to plug in k here, plug in chug. And what we're going to end up getting is, well, that's just going to go to 0 first off, because k minus k is 0. But the bottom, we're not going to get 0, and on the top, we aren't either. So the top is pretty straightforward. So I'm actually going to start with the bottom, just get that out of the way. So we have an e to the ki over our e to the k minus e to the minus k. Now one thing we can note about k here is that, again, by definition, it is just pi over 2 plus pi n. But I'm just going to factor out this I here. And one thing you will notice, actually, is that this looks very similar. This looks very similar to the definition for sine. So sine right here, sine of just some x, is actually equal to e to the xi minus e to the minus xi, all divided by 2i. And if we plug in k here, you'll notice that this right here is sort of like our x, and that we're just missing this 2i, but we can just kind of add that in, can't we? So what we're going to do is, this is the same thing as e to the ki. We'll keep the k on the top just for now. It's going to be equal to, and then we have 2i here, and then we're just going to have a sine of pi over 2 plus pi n. And again, the reason why this is true is that we have like an I here. The I in our k here acts as like that in the exponent, allowing us to express this in terms of sine. And yes, so I'm actually going to expand out the k here in the numerator now. So we're just gonna have a pi over 2 plus pi n, and we have an I, but we also have another I squared is -1. Throw in that negative there. Okay, and so these here are our residues right here. This is the expression for our residues. So now the only thing we have to do is just add all of them up. Easier said than done. So what we're going to do is, I'll go back up, I'll go here. So we have now we just need to find 2 pi I times the sum of our residues. But this right here is just going to be 2 pi I times, well, first off we have an over 2i, so cancel, cancel, cancel. And we have an e to the minus pi over 2 plus pi n, all divided by our, well, so we have a sine, right? We have a sine of pi over 2 plus pi n. So let's really think about what this is saying right here. If we plug in 0 for this expression, we get what? So for n equals 0, we get a sine of pi over 2, that's just 1. Okay, we plug in 1, we get a sine of 3 pi over 2, that's just -1. If you plug in 2, you're just gonna get 1 again. So basically what this is equivalent to, because n is an integer, this is just -1 to the n. So we actually don't need a fraction bar right here. I'm just going to write -1 to the n. And of course we're summing over n. And yes, so to make this, just kind of to clean this up, we're going to have a pi. I don't like that pi. And then by properties of exponents, we can kind of take this out. So we have an e to the minus pi over 2 times the sum from n equals 0 to infinity of e to the minus pi n times -1 to the n. Now the reason our bounds are from n equals 0 to infinity, I'm going to just kind of scroll back up to the contour here. The reason for that, I'm going to erase this little circle right here, is because we're only going to consider our poles that are actually enclosed within the contour. So that would include this one right here, this one right here. So this is, say this is like pi I over 2. This would be like 3 pi I over 2, right? And we're just stacking them on top of each other. We don't really care about the ones that are below the axis here, because those aren't actually in our contour. We don't care about those. So we're just going to start from n equals 0 and then go all the way up to infinity, because we have, well, this is kind of like an infinitely big contour. We're going to enclose, well, all of our poles. So yes. So now all we have to do actually is evaluate this infinite series right here, which might look pretty daunting, but it's really just a geometric series. So I'm just going to kind of evaluate this on the side. One thing we can do by properties of exponents actually is, well, e to the minus pi, e to the minus pi n. This is just the same thing as e to the minus pi to the n. And you'll notice here that we have like n's. We can just kind of group those together. So what we have here really is the sum over all n from n equals 0 to infinity of minus e to the minus pi to the n. And you'll know by the formula for geometric series that, well, first off, you should probably check that this is less than 1, but it should be pretty clear that this is just less than 1. But basically what we have here is, we just have a geometric series. So what we're going to do is use the formula, which is 1. Because if you plug in n equals 0 here, you get 1. You get a 1 over 1 plus e to the pi. Minus pi, I'm sorry. So I'm just going to sub that back in to our original function, or original expression. So you have a pi e to the minus pi over 2, did I get that right? Yes, I did. Over 1 plus e to the minus pi. Now, you might be thinking this is kind of ugly. And it sort of is. But it also is cool that we have each of the pies. That, that counts for something, right? But we can clean this up, I suppose. Though if you want to like impress somebody, you could just leave it like this. But anyway. I'm just going to multiply the top and bottom by e to the pi over 2. E to the pi over 2. This will clean things up quite nicely. So this right here is going to be equal to pi over e to the pi over 2 plus e to the minus pi over 2. Which is cool, but you also might be noticing that this right here, well, that looks awfully similar to hyperbolic cosine, and yes, you would be right, actually. So what we're going to do is, I'm just going to say, okay, put a 2 there, put a 2 there, it's hyperbolic cosine now. So now we have a pi over 2 times 1 over cosh, well, cosh of pi over 2. But we can actually just express this as pi over 2 times the hyperbolic secant of pi over 2, because that's what that is by definition. And there we go. There is our answer to this awesome little integral here. So yes, I hope you enjoyed. The next video will hopefully be a variation of this as well, because it's the same thing but with sine, and it's a very similar process, but there's a tiny difference, which is also really fun. So yeah, I hope you all enjoyed, and I'll see you in the next one. Adios.